Hello, in this video, we will continue our discussion on reactions of aldehyde and ketones as part 3. In our part 2, we discussed about the reactions of aldehyde and ketone with primary amine uh, as the formation of imine, and this reaction we call shift-based condensation. We discussed this reaction including its mechanism. And what we learned is if we have aldehyde or ketone RCOH or R prime, H for aldehyde and R prime for ketone, and if we react with a primary amine H2N, say R prime or double prime, then what happens is it loses the water molecule, and normally this reaction takes place in presence of little bit of acid catalyst. So water molecule will be lost and it result in the formation of RCH or R prime double bond N and R prime. So this is what we call imine. The product with C double bond N we call imine. So when we are running this reaction or when we are carrying out this reaction with primary amine, to result in the formation of imine, this reaction is called shift-based condensation. Shift-based condensation. But this reaction is not restricted to the primary amine only. So again, this reaction we can extend for other type of amine system also, right? So in this case, if we use any aldehyde or ketone, right, H or R prime, and we use the system containing S2N NH2 group, and the other things can be in the primary amine it is R, but it can be any other group, say G can be any other substituents you can have, any other group you can have. The reaction takes place exactly in the same way. It will undergo condensation, but please be aware that we do not, when this G is not alkyl group, we do not call that as shift-based condensation. Shift-based condensation is only for the primary amine. But if you have any other group, like G can be any other group, then it is just the formation of imine. So the result will be again RCH or R prime, and it will be double bond N, and that you have whatever G group that you are using, that will be connected to nitrogen. And this G can be varieties of group. For example, it can be like the OH group. If you use G as OH, then the reactant is H2NOH. This is what we call hydroxylamine. Or it can be, say for example, other NH2 group. Then the result here is H2N NH2 is the reactant. That is what we call hydrazine, and this one is hydroxylamine. We can do the reaction with varieties of other groups, like say for example, G can be like H2, this is the H2N, and G can be NH and other, say for example benzene ring, right? So here instead of NH2 there is only NH and one hydrogen you replace by benzene ring, and the reagent then it will be what, H2N NH with the benzene ring. We call this as phenylhydrazine. Or it can be the other reagent, say for example HN, and you have phenylhydrazine, but in 2 and 4 position we have nitro group. Then the reagent becomes H2N NH. We have the benzene ring with NO2 group in 2 and 4 position. This is what we call 2,4-DNP. 2,4-DNP means dinitrophenylhydrazine. In position number 2 and 4 we have 2 nitro group. Therefore the name is 2,4 dinitrophenylhydrazine 2,4-DNP. This is N, so it can be any G group, varieties of G group that we can use. Say for example, suppose we are using a ketone, say cyclohexanol, and the reaction that we are using with like S2N, NH, and say phenylhydrazine. So you are asked, okay, give me what is the product. So how we do this? Just you focus on NH2, and you'll the water molecule condensation reaction happens, and the water molecule is lost, and you draw this 6-member ring, double bond N, and you have other remaining part is as it is. So this is like a derivative of phenylhydrazone. So this is how you get the product. Likewise, say for example, you have a 5-member ring, and you have somewhere here, suppose you have this aldehyde. Then you are reacting with hydroxylamine, and you are asked, okay, give me what is the product of this reaction. Then what we do again, carbonyl group with NH2OH. You lost this water molecule, the condensation reaction, and the other result is you have a double bond N and OH. So this is how you predict the product. So this is the reaction again with different amine derivative to get the imine derivative complex. This is very similar to shift-based condensation again. The shift-based condensation is just for the primary amine, but the other type of reaction is extended to any other type of the amine here. Okay, so this is one very popular reaction, very important. And by the way, this is the test that we call DNP test for aldehyde and ketone also. Now, the other very popular reaction that we do here is the reactions of aldehyde and ketone reactions with alcohol. And by the way, with alcohol, it will form the product called acetal. So we can discuss this as the formation of acetal. Okay, this is other very important class of the reaction here for the aldehyde and ketone. So what happens here is when you have aldehyde or ketone, right here, H is for aldehyde or R prime will be for ketone. And if we react this with two equivalent of alcohol, R prime OH, it will need two equivalent, and we will discuss about that why we need two equivalent. Okay, and this also reaction takes place in presence of little bit of acid. Then what happens is R C H or R prime, and you have two alcohol groups in this carbon. The alcohol will deliver a R prime O group, so you will have like alkoxide group. Two of this will be attached on carbon. This is what we call acetal. So this will result in the formation of acetal. Okay, so in carbon, instead of C double bond O, two alkoxy group R prime O group will be attached to the carbon, and we call that as the acetal. All right, and this can be both for aldehyde and ketone. Now let us try to discuss how that happens and what is the importance of these reactions there. So we will discuss that with the mechanism, how this reaction happens. Let's talk about the mechanism. First of all, you have your aldehyde or ketone, and since this reaction takes place in presence of acid, so with H plus, you will protonate this oxygen, and we get, again, remember that whenever we do the reaction in acid catalyst, so it will be always plus. Okay, OH plus. Now the next here, alcohol, as you can know that you know by now that this oxygen has lone pair of electron, can act as a nucleophile. So this nucleophile then will attack on carbon, so that this plus charge will be neutralized. The result now is RCH or R prime, and you have now this converted into OH, and you have it has here O H, and at the same time you have your R prime also. Now look at this. This oxygen has now 3 bond, so it has to have the formal charge of plus in oxygen. Now the next step is we don't want it to have this kind of charged species as an organic product, so we deprotonate that to remove this hydrogen. So you can use any base to grab this proton and deprotonate that. So the result is RCH or R prime, and you have your OH, and here is OR prime. Now this is the one you have one alkoxy group. Now you have it has. So this is when we call this as hemiacetal, half of the acetal. So it is hemiacetal with one alcohol group or alcohol molecule. It results in the formation of hemiacetal. Now, if you wanted to substitute the other OR prime or alkoxy group, then you need to carry on this reaction here. So you continue that. First of all, we'll remove this OH group. For that, first you need to protonate that because OH is a poor leaving group. So first protonate this because it is in acidic condition, so you can easily have that H. So you have H or R prime, and then this now becomes OS2 plus, which is a good leaving group now, and you have OR prime. And now you can make this water leaf, so you can easily have that lone pair of electron you can use from this oxygen to make the double bond, and this water can live as a leaving group. Then the result here is RC, and you have a double bond O R prime with the oxygen having plus here, and H or R prime depending upon aldehyde or ketone. Now here you have the OR with the plus charge, then second molecule of alcohol, say R prime OH, will able to attack on this carbon, so that plus charge will be neutralized. And you carry on the same reaction here one more time, CH or R prime. So you have your OR prime, you have added another molecule of R prime OH with the plus in this. Then ultimately you use a base to deprotonate that, so this will grab the proton and this will be neutralized. So you have RCH or R prime, you have OR prime, and other is OR prime. So this is how you put two alkoxy group, and we call this as acetal. So this is the complete mechanism for formation of acetal. You have to do the same reaction twice in order to put two alkoxy group. Now the question is, so what? So what is the application of this? So it's a very, very important application here is you can make what we call is cyclic acetal. We can create the cyclic acetal if we use the two OS group on the same molecule. So this is the one what we call is ethane diol, two OH group with the two carbon, it is called ethane diol. So if we use this ethane diol as a two alcohol group, then it will form what we call is the cyclic acetal. Say for example, if you have C, it can be either aldehyde or ketone, double bond O, then you are reacting that with, say for example, ethane diol. Again, two OS group on the same molecule. And this reaction takes place, as you know, that in a little bit of acidic condition. So what happens is this one here, you add two OR group, but it is connected. So you have two oxygen that will be connected with the two CS2 group. So this is how you get this cyclic system. We call that as cyclic acetal. And this cyclic acetal has a very big application because this cyclic acetal, once you make it, you can easily remove this upon hydrolysis. If you do acid hydrolysis, you can remove that this